In example 7.6, we have G defined for us. G has a domain of all real numbers greater than or equal to -3, and an equation of g of x equals the square root of x plus 3. We are being asked to find the difference quotient of g and simplify. So we know that our difference quotient, dq, is g of a plus h minus g of a all divided by h. So we'll want to come over here to the side and look specifically at g of a and g of a plus h. G of a is going to be the square root of a plus 3. And since the a plus 3 is underneath that square root, it's all grouped together, there's nothing more I can do. And same thing ends up happening with g of a plus h. I'm going to have a plus h plus 3 underneath the radical, and all of that is grouped together, and there's really nothing more I can do. So these are already simplified. Let's bring them over and have them be a part of our difference quotient. So this will be the square root of a plus h plus 3 minus the square root of a plus 3 all divided by h. And in the previous examples, 7.5 and 7.4, we were doing difference quotient calculations, and there's always two rounds of cancellation. There's a cancellation from the subtraction due to the difference, and then there's subtraction from the quotient due to the fraction bar or the division that's going on. And in each of those examples, we started with cancellation due to the subtraction. But the problem here is that I won't be able to cancel the a's and the 3's because of this subtraction. And the reason why I can't do that is because the a plus h plus 3 is all grouped together underneath that radical, and I can't separate any of those pieces for subtraction. And the same thing is true here with the a plus 3 under the radical. I can't separate out those pieces for subtraction. So this gives us a chance to be able to be a little more creative. So I want to make a side note over here about something called a conjugate pair. So a conjugate pair is a pair of factors that look almost identical to each other. The terms will be identical in the two factors, a, b, a, b. But the operation in the factor will be different. One will be an addition, the other will be a subtraction. So when you have a conjugate pair like we've created here, and you go through the distribution process, you will end up with a squared plus ab minus ab minus b squared. And it doesn't matter what a and b are, if you're going to have a plus ab and a minus ab, that's going to cancel out. So every time you multiply conjugate pairs, that's going to happen, and you're going to end up with a squared minus b squared. So this basically serves as sort of a shortcut. Anytime you want to multiply something that looks like a plus b times a minus b, you can just go straight to this as the result. You don't have to go through the entire distribution if we already know what the final answer is going to look like. Now you might be asking yourself, why are you interested in something like this? We're trying to do subtraction. And it's a great question. And the reason why is because I can't do the subtraction the way that I want to. The square root is keeping all that stuff locked up, as we said. So I have to get creative in the way that we get around that issue. And the conjugate pair is the way that we do that. So I want you to watch. Everything in the numerator here is grouped together as one giant factor, if you will. And then I'm going to multiply by another factor, and it's going to be almost identical to this one, except I'm going to put an addition in between my two radicals. This creates a multiplication of conjugate pairs. Now I can't just do that for free. I can't just decide I want to multiply by this for free. I have to also divide by it, so that way I'm multiplying by a creative 1. So the denominator also gets multiplied by this, but in the denominator you're not going to be multiplying conjugate pairs, because you're going to be taking this h and multiplying it with the expression that we just created. So those are not considered conjugate pairs like we have in the numerator. So let's start working on the numerator. So for the numerator, according to what we came up with about conjugate pairs, I should be able to take the first term, which is the radical square root of a plus h plus 3, and then I need to square that. And then I'm going to subtract the second term, which is the square root of a plus 3, and I need to square that. So that's the quickest way to get that conjugate pair multiplied together. In the denominator, I'm supposed to be using my expression that's written in red and multiply it by h. So I'm not going to actually do the distribution. I'm just going to say h, and then I'm going to let the parentheses say times, and I'll copy down square root of a plus h plus 3 plus the square root of a plus 3. So it's going to look like that. Now there'll be a reason why we're not doing the distribution with the h, and that'll become very clear here very soon. So now that we've gotten the creative part of the problem out of the way, now let's go back to just pure simplifying using the operations that are there. So now we have in the numerator two square roots that are both being squared. Well, when that happens, the square root and the square cancel each other out. Those are operations that are called inverse operations of each other, and so they just poof, cancel each other out, and that means that we are going to be left with a plus h plus 3 minus a plus 3, all divided by h times our radical expression. And remember, the reason why we couldn't cancel out the a's and the 3 was because they were locked up underneath the square root, all grouped together. But now that we've gotten the square root to go away, I can cancel the a's and I can cancel the 3's. So then the only thing that I have left, the only term that's left in the numerator now, is just h, all divided by h times our radical expression. That should be a plus. And this is why I didn't want to distribute the h, because now I can cancel the h's. This would leave me with 1 divided by the square root of a plus h plus 3 plus the square root of a plus 3, all in the denominator, provided that h does not equal 0. And that is the difference quotient, completely simplified, for g of x equals the square root of x plus 3.